So why don't we just try a quick question with this. A peak in the beam of visible light travels through polystyrene at a speed of 1.89 times 10 to the 8th meters per second. What's the index of refraction of polystyrene? This is really simple, but so you guys should be able to do this in, say, 30 seconds. It should be, and still we get some people who don't quite get it right. 1.59. Okay, but these are the people who are probably asleep and just clicking something just to keep going, but that's okay. 92% of us say that it's 1.59, which is correct. We just take the speed in light, divide by the speed in polystyrene. You can find the ratio. It's about 1.6. Okay. All right. So all well and good. Now, if we go back to our, let's run this program again. We said that these wavefronts change direction, right? The direction of propagation actually changes. The light rays bend inside the material. So these red lines are the light rays. They change direction. And this is a phenomena called, in fact, refraction. Okay, so the index of refraction has to do with this phenomenon. And so what we want to do is see how much, or at least see if we can quantify how much the light rays are bending when we go from one material to another. So I'm going to go through a little derivation here, doing some geometry mostly. This is in the book. It can get a little hairy kind of drawing all this out. So if you just want to kind of see how it's done, not worry too much about copying it all down because it is in the textbook. But I'll just show you where this comes from. Here's the interface between the two materials. Okay, so here's the interface. And this is, call it medium number 1 and medium number 2 on this side. And what I'm going to do is basically zoom in on one point or one part of this diagram here and show these wavefronts coming in right at the surface. And let me draw these in different colors here. So here is, in the first medium, we have a wavefront, and then another wavefront, and this perpendicular distance between the two wavefronts is the wavelength. So this is lambda 1. Okay? We'll call this angle theta 1 between the surface and the wavefront. Okay? Now we see that those wavefronts bend a little bit, so I'm going to draw those in the new material. Here is a wavefront. Here's another wavefront. And say another one up here maybe. We can draw this. Try to draw a wavefront way up here, about the same distance away, and another wavefront here. And this perpendicular distance is the wavelength in the second medium, so I'll call that lambda 2. Okay. So the way to think about this is this wavefront is traveling this way, and it bends inside here, and this wavefront is traveling this way now. And they share, if we look at these two triangles. So here's a right triangle, and here's another right triangle. And let me call this angle theta sub 2. And this side that's shared between them is D. Okay? We do a little trigonometry. We say, okay, look at this, this right triangle. We have the opposite side over the hypotenuse is going to give me the sine of the angle, so I can say that sine of theta 2 is lambda 2 over d, but sine of theta 1 is the same thing. Sine of theta 1 is lambda 1 over d, and d is the same. That hypotenuse is the same for those two triangles. So I can do a little rearranging here and come up with that d has to be equal to lambda 2 over sine theta 2, and that's got to be equal to lambda 1 over sine of theta 1. So those two things are the same. We also say that, again, the wavelength is going to be equal to the speed, v1, times the period, or speed divided by the frequency. And the period and the frequency are the same for both materials. So I can say that we have v1 t over sine theta 1 is v2 t over sine of theta 2. And the t's cancel out. And then by definition, we said that this index of refraction is c over v, so n1's index of refraction is c over v1, and n2's index of refraction is c over v2. And if I plug that in, by just saying v1 is c over n1, plug that in, I'm going to get c over n1 sine theta 1 is equal to c over n2 sine theta 2, and the c's will cancel out. And so we're left with this relationship. n1 sine theta 1 is equal to n2 sine theta 2. If I do a little geometry, now I measured these angles from the interface. If I do a little geometry, I can show, I'm going to draw a line that is perpendicular to the interface between the two materials. Okay? You can show that this angle between this light ray, because again, the line perpendicular to the wavefronts is a ray, so that's a ray. And here's another light ray. That's the ray in the second medium. If I draw a line from the perpendicular to the ray, I'll call that the angle, the incident angle. And that's theta the same as theta 1, and this is the same as theta 2. So we can quantify how much, if I know the index of refraction for the two materials, and I know how much the light ray bends in one medium, I can find out how much the light ray is going to bend in the second medium. This is called Snell's law. And it's just the basic law behind this field of geometric optics. It says, it's telling us how much the light ray bends, the light ray bends from the normal. And that normal is a line that's perpendicular to the surface, perpendicular to the interface between the two materials.